Okay, so this chapter we are already done with heat transfer actually. This chapter is about mass transfer. Okay, and this is just one chapter, a small one, not really a big one. So we are done with the conduction, convection, radiation, and now this is diffusion mass transfer. So let's start with this chapter. So we are going to cover physical origins, mixture, composition, talk about the fixed law of diffusion and mass diffusivity, and rest of the chapter is for you to read for yourself. Okay. What was the law for conduction? What was the name of the law for conduction?
Fourier's law.
Fourier's law. What was the name of the law for convection?
Newton's law of cooling.
Law of cooling. What was the name of the law for radiation? Stephen-Boltzmann law. And the law for the mass transfer. Law for the mass transfer is Fick's law of diffusion. Fick's law of diffusion. That's for the mass transfer. Okay. Anyways, the three fundamental transfer processes are there. First one is the momentum transfer, which you studied in the mechanics. Then the heat transfer, which you studied from chapter 1 till chapter number 13. And then this is the mass transfer. Okay. So momentum transfer takes place if there is pressure difference, or in other words, one side force is applied, other side force is not there, body will move, momentum will transfer. Heat transfer takes place when there is temperature difference. However, mass transfer, now there is a little confusion here. Confusion because when we studied convection, so there was the wind blowing or the water flowing. So there is mass transfer, but we are not really concerned about that mass transfer because all of those mass transfers are because of external means. Something is instigating that. So you put a pump, so it is making the flow. So that's an external force which is making the flow. Okay. Or for example, you put a fan and that is making the air to blow. Okay. So again, this is an external means. So that was all about the force convection. There is mass transfer, but that's not the mass transfer. We are producing that mass transfer by external means. Okay. So we are not talking about that mass transfer here. Now there are some other type of mass transfer where we are not directly involved in producing the mass transfer. For example, natural convection. Now in natural convection, in free convection, natural convection, there is no external means, no fan, okay, no pump. But what happens is that we are producing the temperature difference, and that temperature difference is producing the buoyancy effect, which is causing the transfer of mass to take place. So again, what we are doing is that we are indirectly making the mass transfer. Because of the temperature difference, because of the temperature gradient that we produce, the buoyancy effect takes place, and as a result, the mass transfer occurs. So we are indirectly responsible here. Okay. So we are also not talking about that. What we talk about is here when we say mass transfer. So what we are concerned here is the diffusion mass transfer. So diffusion mass transfer occurs whenever there is a difference in concentration of different species from one point to other point. Okay, then we have diffusion mass transfer. So a very common example is given, like if you have a cylinder, okay, suppose I have a cylinder or I have a box, okay, on one side I have oxygen, on other side I have nitrogen, okay, and I just put a small hole here. So what will happen? Automatically oxygen and nitrogen will mix together. Suppose both are at same temperature and there is no pressure difference. Still oxygen and nitrogen will mix together. Why does this mixing occur? So because of the random motion of the molecules. Some molecules of oxygen will move towards the nitrogen, some molecules of nitrogen will move towards the oxygen, and this movement is occurring because of the concentration difference. So there is 100% oxygen, there is 0% oxygen, there is a concentration difference. Nature tends to equalize things. Always it's like that. Nature tends to equalize things. Why does heat transfer take place? When there is temperature difference. So want to transfer some heat from one part to the other part so that the temperature equalizes. Why does the flow occurs? Because there is pressure difference. So there is high pressure, low pressure wants to transfer some of the flow from high to low so that the pressure equalizes. Okay? So all the time, whenever there is a motion, it's governed by the nature on the phenomena that nature wants balance. Okay? So that's the thing here. Now if there is concentration difference, although there is no temperature difference, there is no pressure difference, still the mixing will take place. It's because of the concentration difference, because nature wants to mix it evenly. And a time will reach, if you leave it for a very long time, a time will reach, then there is 50% oxygen and nitrogen in this part, 50% oxygen and nitrogen in this part, and then this transfer will stop. Okay. So this continues till there is concentration difference. So what we are specifically talking about when we talk about the mass transfer, it is this diffusion mass transfer. Okay, it is this, the diffusion mass transfer that we are concerned of. So suppose you have an ink which has approximately the same specific gravity as that of the water, slightly different, okay, and you put it into water. So you will see the ink will start spreading in the water. That's by the diffusion process. The temperature of the ink and the water is the same. Okay, we are not producing any pressure differences here. It's just because of the diffusion process. Random molecular motion, ink will continue to spread inside water. If you keep it for a very long period of time, a time will reach when ink will be equally distributed within water. So it will be like bluish water if you put blue ink in the end, okay, with equal distribution. So that's the law of the nature. So when we talk about mass transfer here, even mass transfer is like misleading because we have been discussing mass transfers a lot. But right now when we are talking about mass transfer here, it's the diffusion mass transfer. Okay? So similarly, diffusion mass transfer takes place if there is difference in the concentration of some chemical species in a mixture. So you have chemical species in a mixture, and if there is concentration difference, so automatically the transfer will occur. Okay. You understand this concept here so far? Okay. Okay, although mass is certainly transferred whenever there is bulk fluid motion, the term mass transfer is not used to describe the motion of air that is induced by a fan or the motion of water being forced through a tube. So we're not talking about if it is motion of air because of fan, or motion of water which is forced through the tube by pump or whatever they mean. Okay, in both cases there is gross or bulk fluid motion due to mechanical work. We are doing some work, pump is doing mechanical work, fan is doing mechanical work. Because of that work, this motion is occurring. Here we use the term mass transfer to describe the relative motion of a species in a mixture due to the presence of concentration gradient. So here we are concerned about the concentration gradient. Okay, most of the time, okay, in real life, where you have seen this mass transfer occurring. For example, you know, sometimes if you go into the market, there are some perfumes. Yes. There's like solid body, and if you just remove the cover from it, so they will keep on with the air. They will keep on mixing in the air, and the mass of the body will keep on reducing until it is finished. Okay, that's the, so the material is kind of volatile. Okay, and it's high concentrated, and in air there is no concentration of it. Because of the concentration transfer, it will occur. Okay, it will keep on diffusing into air, a time will reach that it will vanish. It will be totally diffused. Okay, so that's one of the day life example that we come across. Moreover, since this mass transfer takes place through the diffusion process, it is more appropriately referred to as the diffusion mass transfer. So basically this is the diffusion mass transfer because it takes place because of the diffusion process. Random motion of the molecules, that's diffusion. Okay, so whenever there is concentration difference in a medium, nature tends to equalize things by forcing a flow from high to the low concentration region. And these are some of the examples where you can see these things happening. Okay, anyways, we move towards. Okay, so consider a tank which is divided into two equal parts by imaginary boundary, each part containing a different matter. It's a similar example, tank divided into two parts, each part containing a different matter. Okay, assume that initially the left half of the tank contains nitrogen. So it's left half nitrogen, right half oxygen. At the same temperature and pressure, still they will mix together because of the concentration difference. Okay. Anyways, we'll discuss this. So mass transfer is a phenomena which occurs in gas, mixture, in a liquid solution, or solid. So it occurs in all the things. So solid also mix because of the diffusion. Liquid also mix because of diffusion, like ink in water. Okay, gases also mix because of the diffusion. Okay, so this process takes place in all the kinds of matters. Okay, whenever there is concentration gradient, it will happen. The species concentration gradient is the driving potential for the transfer. So concentration gradient is the driving potential here. Diffusion occurs more readily in gases than in liquids, and more readily in liquids than solids. Obviously, because it's a random motion of the molecules. Random motion of the molecules is more quick in gases compared to the liquid, and solid, it's very slow, very slow. Okay. The basic mechanisms are the same whether the phase is gas, liquid, or solid. Mass transfer by diffusion is analogous to heat transfer by conduction. That's a very important point. In fact, your fixed law of diffusion, you will understand it much better because this fixed law of diffusion is very similar to the conduction law. Conduction and diffusion, we discussed, it's the same thing. In fact, conduction and diffusion, it's the same thing. Two names for the same word, right? So when we talk about diffusion mass transfer, it's very similar, analogous to conduction. Conduction, mass transfer are very similar. Like any other transport phenomena, the molecular transport process of mass is characterized by the general equation rate of transfer process equals to driving force over resistance. So flow rate is equals to the driving potential divided by resistance. In case of the heat transfer, the flow rate was a heat transfer rate. Driving potential was the temperature difference. And resistance is what you know. Okay. We discussed about resistances a lot. Okay, now there are certain definitions here, to certain terminologies which are important, which you will be using. Okay, first is the molar concentration. So molar concentration. Okay, the unit of the unit of molar concentration is mole, not kilomole. So it's written wrong here. It's basically mole, not kilomole. But yeah, sometimes the values are in kilomole. But the basic unit you should know. For example, the basic unit of mass is what? Kilogram. It's kg. It's not g. Sometimes the mass could be in g.
Maybe in their table.
Okay. But anyways, so the basic unit is mole. So mole per meter cube is molar concentration. Mole per meter cube is molar concentration. It's close to density. Okay, so density is kg per meter cube. Here we are talking in terms of the mole instead of kg. Okay, so we have this formula. So C is equals to density upon molecular weight. So this is the molecular weight. Okay, molecular weight is kg per kilomole. Okay, so the relationship between density and the molar concentration is this. Or density is what? Mass upon volume. I can write here as mass upon volume multiplied by the molecular concentration. Okay, just like that. Or here also we can write here as okay. Now we know that PV is equals to nRT, right? Let's say if it is gases. Let's say if the diffusion process is for gases. So PV is equals to nRT. So okay, M upon M. This is what? Mass over molecular weight, molar mass. So that's N, right? So this thing can be written as N upon V, right? Or from, if it is gases. If it is not gases, then you cannot apply this. But if it is gases, an ideal gas, assuming ideal gas, then we apply PV equals to nRT from thermodynamics. Okay. So N upon V will be what? N upon V will be P upon RT, right? So I can write here Z is equals to P upon RT. Okay. So this is P. So anyways, so we have this molar concentration, this mass density, the regular density that we know. Then we have the molecular weight. Okay. Another important terminology here is the mole fraction. Okay. So mole fraction is what? Mole fraction is the moles or molar concentration of something divided by the overall molar concentration. So you have a mixture with 2, 3, 4, how many number of species. So concentration of one species divided by the overall concentration. That's the fraction. It's like a percentage in moles, percentage. Okay. So if it is for the case of solids, we represent it by xi. Xi is equals to Ci upon C. Ci means the concentration of a specific component, and this is the overall concentration. So it's fraction, it's like a percentage. And if it is liquids or gas, if it is solid or liquid, represented as X. If it is gases, we represent it as Y. So Yi is also Ci upon C, but if it is gases. Okay. Mass fraction. So it's again a fraction, but in terms of the mass. So percentage in terms of mass. So mass of one component divided by the overall mass. Previously that was for the mole. Okay, this is for mass. Mass fraction of a species. Then we have the molar flux. The molar flux is a very important parameter because this is the one which we'll be using, because here in the previous case we had temperature difference which is causing the heat transfer. Now we have concentration difference which will cause the species transfer. The species transfer is known as molar flux. How much is one species transferring from meter square area from one part to the other part? That's the molar flux. It's due to diffusion. So molar flux is kilomole or mole per second meter square, or mass flux is kg second per meter square. Okay. Anyways, so these are some of the definitions important. Okay, here we know that for example, for the case of gases, this is for liquid and solid, but PV equals to nRT is only for the gases. Okay, so for the case of gases, Yi is equals to Ci upon C, or C is equals to P upon RT, right? So I can write here Yi is equals to, so Ci will be Pi upon RT divided by C will be P upon RT, right? Because we are talking about the diffusion mass transfer, so actually there is no temperature gradient, so temperature is same. Okay, so R is also same, temperature is also same, it will cancel. So it's actually the partial pressure of one gas divided by the overall pressure. Okay, so if I have a container which is having a pressure of 2 bar and having 50% oxygen, 50% nitrogen, then the partial pressure of oxygen will be 1 bar, the other partial pressure of nitrogen will be 1 bar. So 1 bar becomes 2 bar. So their molar concentration or mole fraction is basically the pressure fraction, the partial pressure of one component. So that becomes Pi upon P. Is this clear so far? We're just discussing the formulas here and the terminologies. Okay, let's move ahead. Okay, the other thing is that the mole fraction, okay, or molar fraction or mass fraction combined for the complete body will be 1. So because fraction is basically kind of a percentage of, so if in a body there is 20% oxygen, 20% nitrogen and 60% carbon dioxide, if you sum them up all together, it will be 100%. So summation of all the mole fractions within the body will give you 1. So summation xi is equals to 1. Summation of all the mass fractions will also give you 1. Okay, in terms of the mass, what is the percentage of one thing within that species? So for example, I have water. In water, I put salt and sugar. Okay, so within the now I have a mixture of salt, sugar, and water. Okay, so within this there is some mass percentage of salt, some mass percentage of water, some mass percentage of sugar, but overall mass percentage will be 1. Okay, similarly overall mole percentage will be 1. So that's an important parameter here. Anyway, these are again the same formulas written back again here. Okay, so let's have an example related to what formulas we studied. Okay, nothing really.
Easy.
Yeah, easy peasy. Okay.
Thin slide, right?
Huh?
Thin slide.
Yeah. Okay, the composition of air is often given in terms of only the 2 principal species in the gas mixture. So we have oxygen here and nitrogen. So what's given is the mole fraction of oxygen and mole fraction of nitrogen. 21% oxygen, 79% nitrogen. Determine the mass fraction. So we know the mole fraction. What we want to know is determine the mass fraction of both oxygen and nitrogen. Okay, and we need to determine the mean molecular weight of air. So mean molecular weight of air. So mean molecular weight of air is this, m, molecular weight. So mean molecular weight of air when it is maintained at 25 degrees centigrade and 1 atmosphere. So we know the temperature and the pressure of the air. The molecular weight of oxygen is 0.032 kg per mole and nitrogen is 0.028 kg per mole. Okay, so we know the molar fraction. So let's say that if we take 1 mole of air, so in 1 mole of air, so if we take 1 mole air, so it will have 0.21 mole oxygen plus 0.79 mole nitrogen, right?
Yes.
That's the molar fraction. If we take 1 mole air, so it will have, according to molar fraction, 0.29 mole of oxygen and 0.79 mole of nitrogen. Since we know what is the molecular weight of oxygen and what is the molecular weight of nitrogen, so we can convert it into from mole to kg. Okay, so for oxygen is 0.032 kg per mole, and for nitrogen is 0.028 kg per mole. We want to know the mass fraction, so first we need to know the masses. Then we can find out the mass fraction. We know the moles, just convert them moles into masses by using the molecular weight. Okay. So for finding that, we have 0.21 mole of oxygen. So multiply it with the molecular mass of oxygen. So mole will cancel, it will be kg. So that is this much amount of oxygen present. Okay. Similarly, for the case of nitrogen, 0.79 mole, multiply with the molecular weight of nitrogen, so we'll get it in kg. So that much kg of nitrogen present in 1 mole of air. Okay. So now we add them together, that will become the total mass. So now we have the total mass if we add together. And then the mass fraction is what? Mass of one species divided by the overall mass. Mass of other species divided by the overall mass. So mass of oxygen divided by overall mass, so it's 0.23. And mass of nitrogen divided by overall mass is 0.77. So basically in air, the mass fraction, in terms of the mass fraction, oxygen is 23%. In terms of the mole fraction, oxygen is 21%. Okay. Is it clear?
Yes, yes.
It's basic chemistry, right? Basic chemistry.
So you have a short of ring it in the final.
Okay.
Or 20.
Okay. Okay, so now we have determined this. So now we have determined this. Now the other thing that we need to find is the mean molecular weight. We can use this formula for air. What's the mean molecular weight for air? So we have C is equals to rho upon m, but we need to find m, mean molecular weight. So let me write here m is equals to rho upon C. Okay. Or rho I can write here as m upon v, right? Now overall mass of the air, we know, we determined it,
Yeah,
0.0288. Overall mass of the air, we determined it. Okay, now what's the volume of the air? Since this is air, we assume it as an ideal gas. We can assume it as an ideal gas. So PV equals to nRT will be applicable, right? We're talking about 1 mole of air. From the beginning, we started with assuming 1 mole of air. So N is 1. So N is known. R is a constant,
Yeah.
which is also known.
Temperature is not.
Temperature is given,
Yeah.
298. Pressure is given. Okay. So temperature is given, pressure is given. We can find out what is the volume of the air, right? So I can substitute the volume here as well. Okay. Now overall concentration, molar concentration of air. Okay. So we know that air is composed of nitrogen and oxygen. So overall molar concentration of air will be concentration of oxygen plus concentration of nitrogen. Right. Concentration of oxygen plus concentration of nitrogen. So you can see here that now concentration is basically what? Concentration is moles, so moles over volume.
Yeah.
Okay. So N upon V,
Yeah.
right? In terms of the moles, concentration is N upon V. So we know what is the mole of oxygen, we know what is the mole of nitrogen, we know what is the overall volume. Okay? So that's NO2 divided by V plus N2.
The overall volume.
Overall volume. Okay? So if we substitute the values here, because we know what is V, we know what is V, we know what is N, we know what is this. It's 0.21 and 0.79, which was given. 0.2. where was, yeah, here, see, 0.7. Okay. So if we substitute the values here, we know what is C. Now we know C, we know V, we know M. We can find what is the mean molecular weight of air. Is it clear? So we have solved this problem. It's more related to chemistry, actually, basic chemistry. Is there anything which you do not understand? And the solution procedure for it. Okay. So now let's talk about the fixed diffusion law. Okay, fixed law of diffusion is what? As I told you, it's very similar, analogous to Fourier's law of conduction. Very similar. What was the Fourier's law of conduction? Can you tell me the formula?
K
Q
equal to K A delta T. V equal to A.
Okay, Ka delta T upon delta T. Or basically the formula was Q is equals to negative Ka in differential format dt by dx. Right? That was the formula for Fourier's law of conduction. Now, as we say that the fixed law of diffusion is very similar to the Fourier law of conduction. Okay, Q upon A. Q upon A is basically what? Q double dash, right? So that was the heat flux. So now we will not have heat flux. We will have the mass flux or molar flux, right? J star, molar flux, is equals to negative K. K was what? K, what's the K? K is thermal conductivity. K is thermal conductivity. Conductivity is like diffusion. But here no thermal conductivity because there is no thermal temperature difference. What's the difference we have here? Concentration difference. So it's the concentration transfer coefficient. So it's basically, we call it diffusion coefficient. We discussed that in the previous chapter when we discussed Schmidt number and Sherwood number. So we said we don't have K, we'll have D. Diffusion coefficient. There is no coefficient of thermal conductivity because there is no thermal transfer, but there is species transfer. So that's the diffusion coefficient for species transfer. It's always between A to B. Hydrogen to oxygen, hydrogen to water, oxygen to water, water to whatever. It's like that. It's always between two, and it depends upon the material. For the case of temperature, it does not really depend upon material, it just depends upon temperature difference. Here it depends upon material as well. Okay? So it's coefficient of diffusion, or basically you can say this, mass diffusion. Mass diffusion. We had thermal diffusion, we had momentum diffusion. This is mass diffusion, and as I told you, for the case of whenever you have diffusion formula, it has the same unit, meter square per second. Thermal diffusion, alpha has meter square per second. Momentum diffusion has the same meter square per second. And this D, again, this is diffusion but for mass. So it's also meter square per second. So here the unit conversion becomes a bit complicated because there you had the watt per meter square Kelvin, right? Watt per meter Kelvin, sorry. Here it is meter square per second. So the units becomes a little fuzzy. You just need to have a little track of it. Okay. Anyways, what's going to be here? dt by dx. So that was the temperature difference with respect to a certain distance. Now we don't have the temperature difference. We have concentration difference, right? So this is concentration. Okay, so d Ci upon dx. Ci is the concentration of one species.
Why is it dx? Why dx here?
I'm going to come to that. Do you understand this so far?
Yes.
I've just made a comparison
Between the two.
between the two, right? Now that's the concentration of one species, okay, along a certain distance. Concentration of one species along a certain distance, okay. So we know that Xi is equals to Ci upon C, right? Overall concentration multiplied by the mole fraction is equals to the concentration of one component, right? So overall concentration is a constant.
Yes.
Why it's a constant? If I have a glass of water and let's say I put ink in it, now initially there is concentration difference of ink from the top to the bottom, then the ink will start diffusing. But whether it is diffused yet or not yet diffused, the overall quantity of water and ink is conserved. It's the same. After it has completely mixed, it is still same. When it has not yet mixed, it is still same. So overall concentration does not change, it's a constant. Even when the diffusion has occurred or if the diffusion has not yet occurred, it's in the process. The overall C does not change. Okay? So I can write here instead of Ci, I can write here Xi into C, right? But this C is a constant.
Out of front.
So this go out. Okay, so I can write C here. So now what's left here is dxi upon dx. But you need to be a little concerned here because the two x's are not same. This x is the mole fraction. This x is distance. So don't think the two x's are distances here. One is the mole fraction, other is the distance. This is clear. So now this becomes our formula for mass transfer, and this is known as fixed law of diffusion. So now the formula matches. J is equals to negative C d dxa upon d dx. Okay. So this is the fundamental formula which we will be using for the case of mass transfer, diffusion mass transfer. Do you understand this formulation?
Yes.
Okay. Now let's talk about the mass diffusivity here, this mass diffusivity. Now mass diffusivity is really a material property. So from which body to what body transfer is occurring, diffusion is occurring. And we have to use the values from the tables. Okay, so within the tables that we have in the appendix, we have the diffusion constant given. Coefficient of diffusion is given. Now, however, when these values are given, you know all of these values are given under a certain specific temperature. These values are given for specific temperature. Now, for the case of mass diffusivity, whenever there is diffusion from a gas to a gas, whenever diffusion between gases, this is heavily dependent upon temperature. But if one of the component is not gas, if it is liquid, solid, then it's not really that much dependent upon temperature. But if both are gases, then it is hugely dependent upon temperature. And the relationship is that this diffusivity dAB is a function of temperature power 3/2. Okay. So you change the temperature, mass diffusivity will change only for the case if the two are the gases which are going through diffusion. Okay. For the case of the liquids, so solids, it's actually much more complicated, and we will assume the same values as we had in the table, irrespective whether the temperature is same or different. But for the case of gases between gases, If the temperature is changed, we have to consider this factor. Okay, so DAB upon DAB 2 upon 1 will be equal to T2 upon T1 power 3 by 2. This means this thing. Okay. So you know the diffusion coefficient at a specific temperature T1, but now your temperature is not T1, your temperature is T2, then you need to recalculate the diffusion coefficient for 2 using this relation. Okay. Okay, let's move ahead. Let's have another numerical. So we have two short numericals here, and with this,
We finished the chapter. We finished the
last number.
no, second last numeric. Okay, consider the diffusion of hydrogen in air, liquid water, and iron. Diffusion of hydrogen in air. So one species is hydrogen, the other species is air, or the other species for the second case is liquid water, and for the third case it is iron. Okay, at 293 Kelvin. Okay, calculate the species flux on both molar and masses basis if the concentration gradient at a particular location is dCA by dx is equals to 1 kilomole per meter cube meter. Compare the value of the mass diffusivity to the thermal diffusivity. The mole fraction of hydrogen is much less than unity. So it's basically this formula that we are concerned here. Okay, or I can say here it's basically this formula. J is equals to D negative DAB dCA upon dx, right? Where we are directly given what is dCA upon dx. Right? We are directly given what is dCA upon dx. So we will just take the value from the table for hydrogen to air, for hydrogen to liquid water, for hydrogen to iron, and substitute here. We know this is 1, and we will get what is the flux. Is it clear? The only catch here is that when it was hydrogen to liquid water or hydrogen to iron, it does not matter what the temperature is. But when it is hydrogen to air, now there are two gases involved, and it does matter what temperature. So you see that from the table at what temperature you are getting the value. And your actual temperature is 293 Kelvin. If the value that you get from the table is not 293 Kelvin, then you need to recalculate
Using the formula.
using this formulation. Only for the case between gases, gas and gas. Is it clear? That's the only catch here. Okay, so you see here they use table A8 to find hydrogen air, but it is at what temperature? 298 Kelvin. Your temperature is 293. Is the temperature difference here? For the case of hydrogen water, it's also 298 Kelvin, but it does not matter because the two are not gases. One is gas, other is liquid. Okay. For the case of hydrogen iron, it's 293 Kelvin. It's already given 293 Kelvin, but even if it was not given 293 Kelvin, still you will take directly the value. It's clear? So,
Doctor, for the 298 Kelvin, what properties I take? Do interpolations?
yeah.
We can assume the 300.
We can view these atoms. What?
For the case of gases, they are hugely dependent upon temperature. So you see here, we already got the diffusion coefficient between hydrogen and air at 298, but we wanted to find at 293. Okay, So use this formulation. Based on this formulation, it will be 293 upon 298 power 3 by 2 multiplied by the value from the table. You will get this. So you recalculated the diffusion coefficient. You recalculated the diffusion coefficient for the case of hydrogen air. For the case of hydrogen water, for hydrogen iron, take the same values. Okay. And now there is another number here which is known as Lewis number. Lewis number is basically what? It's a ratio of thermal diffusivity to mass diffusivity. Ratio of thermal diffusivity to mass. How quickly the thermal energy is diffused divided by how quickly the mass is transferred. Okay. So if you have a case where there is concentration difference, along with that there is temperature difference. So both of the thing will diffuse.
Looks like K mu over alpha.
Yeah. Okay. So, but that mu over alpha is the Prandtl number.
Yes.
This is Lewis number, but it's the same concept. Okay. Ratio between two diffusivities. Okay. So how quickly the heat will transfer divided by how quickly the concentration mass will transfer, species will transfer. Okay. And Lewis number for gases is almost of the order of 1. So the mass transfer or species transfer and the thermal transfer is almost at the same rate for the case of gases. But for the case of liquids and solids, the thermal transfer is very quick. The conductivity is high. Okay. However, mass transfer is a little slow. And in case of solids, very, very, very slow. Because solids very heavily packed atoms does not allow them to move much. Okay. Physical significance. Okay, once we know that, so just substitute the value here. So you will get the molar flux. Okay, and if you multiply the molar flux with the molecular weight of hydrogen, you will get the mass flux. Mole and mass are related with the molecular weight. So you get the molar flux, multiply with the molecular mass, molecular weight, get the mass flux. Okay, so for the 3 cases, it's given. Okay, in the form of a table, it's given. But anyways, if you don't write it in the form of a table, one by one, it's okay. Then there is a little discussion about it. You're going to go through this discussion yourself. Okay. Okay, let's have the last problem. A mixture of helium and nitrogen gas is contained in a pipe at 298 Kelvin. So we have a mixture of helium and nitrogen gas which is contained at 298 Kelvin and 1 atmosphere total pressure, which is constant throughout. At one end of the pipe at 0.1, the partial pressure of helium is 0.6 atmosphere, and the other end it is 0.2 meter apart. Partial pressure is 0.2 atmosphere. Calculate the flux of helium at the steady state if the diffusion coefficient of diffusion of the helium to nitrogen mixture is 0.687 newtons per minus 4 meters square per second. So the thing is that we have a pipe, and the pressure inside the pipe is same. Overall pressure inside the pipe is same, but inside the pipe you have helium and oxygen. Sorry, helium and nitrogen. Okay, so if we take the partial pressure of helium at one point and partial pressure of helium at other point, and how much is the distance between the 2 points? 0.2 meter apart. Okay. At this much distance apart, there is a difference in the partial pressures of helium. Okay, so here the partial pressure of helium is 0.6 atmosphere. Here it is 0.2 atmosphere. Okay. So you know that molar concentration for the case of gases is proportional to pressure, partial pressures. So if there is a difference in pressure, partial pressure of helium, that means there is a concentration difference from one point to another point. So we need to find out what is the flux of helium. Obviously helium will transfer from here to there. Although the overall pressure is same, there is no overall pressure difference. Total pressure is same.
Because of the partial pressure.
But the partial pressure of helium is different. So helium will transfer from here to there, and the nitrogen will transfer from here to there. Okay, so we need to find out that flux. Okay, so that flux will be what? So I can write here J star is equals to, let's take the C again inside. Okay, so negative DAB DC CI upon dx, right? That's what we started from. Okay, or I can remove the negative sign here, and I can just say it is concentration, the difference between the two. When we remove, when we have this formula and we remove negative sign, we just say it is delta T. So it is delta concentration. Okay, delta concentration overall the distance divided by the distance. Okay, so I can write here as DAB concentration difference, concentration of helium 1 minus concentration of helium 2 divided by delta X, right? Now concentration, since this is helium, this is a gas, it's a function of pressure, so it's a function of partial pressures. Okay, so C is a function of pressure by this term, P upon RT, right? So I can write here as DAB. Now C is P upon RT, this C concentration is again P upon RT, but RT is same, it's just the C which is changing. So it's C is related with P, so partial pressure. So partial pressure of helium at 1 minus partial pressure of helium 2 divided by delta X divided by RT, right? So we know what's the partial pressure here, 0.6 atmosphere. Obviously we have to convert it into basic unit of pressure, which is Pascal. Then we know what is the partial pressure of helium here. We know these things.
Yes.
We know diffusion coefficient. We know the distance. We know R. We know the temperature.
That's all.
Just substitute all the values and that's it. We find out what is the flux of helium. So with this, it's just conversion from 0.2 atmosphere to Pascal, 101.101325, multiplied with 101325. And that's it. Once you do this, that's the end. So your chapter number 14 is
21.
done.
Each one of us have to solve five homeworks, right? Can we solve this?